In this lesson, we will study how we can monitor rates of chemical reaction.
In some reactions, it's really easy to see the reaction progressing. Sometimes we can see a gas being produced. Sometimes we can see a change in temperature. And sometimes we can see a change in colour. Measuring a rate of reaction is a really crucial part of chemistry, especially in a chemical plant. If a reaction is exothermic, then it generates heat as it progresses. And then, not understanding the rate of reaction could lead to a huge buildup of temperature and pressure. And then, in the reactions that we've just seen, the changes are quite gradual, and that can make it difficult to know when the reaction is finished. It is possible to measure the rate of reaction if we have the right kit. For a reaction which produces gas, like this fizzy aspirin tablet, we can measure the volume of gas that is produced. We have a rate of reaction. Unfortunately, the units of milliliters per 10 seconds are not very useful, so let's convert them. First, we'll convert it into milliliters per second. Now for the tricky bit. We want to know how those milliliters relate to the molecules reacting in the flask. We know that 1 mole of gas at standard temperature and atmospheric pressure takes up 24 decimeters cubed of volume. That's 24,000 milliliters. Our number is quite a bit smaller than that. We haven't produced a whole mole of gas molecules yet. So we can take our number of milliliters and divide it by 24,000 to get the number of moles of gas we have produced. So now we've calculated our rate of reaction in moles per second. Measuring the rate of reaction in this way is quite simple because we can measure the volume of gas that's produced. But what about a reaction where a colour change happens? Well, we can use a colour scale, such as with pH changes and an indicator, or we could use a colorimeter. Matching the colour change onto the chart can be quite difficult because the changes are so gradual.
When you measure the rate of reaction, you're measuring the speed at which a product is formed or a reactant being consumed. Although it is very difficult to monitor a specific chemical, as reactions are often a confusing mixture, but quite often we can observe obvious properties that are easy to measure. Graphically, if you're measuring changes happening to a product, you will see an increasing pattern in your graph. If you are measuring a reactant, then you will see a decreasing pattern. Often the patterns are not directly proportional to time, so you will end up with a curvature. The graphs will usually have a steeper slope initially, then taper off and create a plateau as the reaction progresses. To calculate the average reaction rate, you can simply use the initial point and the final point to draw a line and find its slope. The slope would be rise over run, where the rise is the amount, changes in the amount, and the run is change in time. To calculate the instantaneous rate, and that is if you want to know how quickly a reaction is happening at a specific point in time, you can spot that point on the graph, draw a tangent line, and find the slope of that tangent line. So let's try an exercise problem. There's a reaction written here. It's between sodium bicarbonate and H positive, which is another way of indicating an acid, because acid is what produces hydrogen ion when dissolved in water. And this produces carbon dioxide gas, sodium ion, which is just a spectator from sodium bicarbonate, and we also produce water. Now, what are some changes we can measure? We can look at the reactant side and the product side. So let's look at the reactant side first. Examining the states of reactants, we have a solid substance and aqueous substance. Aqueous means it's well dissolved in water, so you probably can't differentiate this hydrogen ion when it's fully dissolved in water. It will just look like water. Whereas solid, it is relatively easy to filter this. So if we set up multiple trials of this same reaction, so trial number 1, trial number 2, trial number 3, and in it we have equal amount of both reactants. First one, we let it run for, let's say, 10 seconds, second one for 20 seconds, and a third one for 30 seconds, and basically filter out after 10, 20, 30 seconds to see how much sodium bicarbonate has been consumed. Another way of measuring reaction rates using a reactant is by using a pH meter. Now, acid has pH below 7 at room temperature, so as you start the reaction and as hydrogen ion is being consumed, the reaction will be less, it will become less acidic over time. So if you were to use pH meter, you're going to start with a fairly low pH because all the acids will have low pH, and as the hydrogen is consumed, the pH level will rise. So you should be able to monitor the pH change over time and use that to measure the reaction rate. On the product side, we clearly have a easy property to measure, which is gas. Now, gas bubbles, and if you can have a system that is open, then it will allow carbon dioxide gas to escape into the atmosphere. So as you lose chemical, the entire system will become lighter. So the mass of the system, which is basically everything, it's going to decrease. So open system is when you have a beaker wide open, there's nothing to cover up, so that's open system. Things can come in or leave the system. Okay, so carbon dioxide will escape, and you will lose some mass. Okay, I don't know how noticeable amount you're going to lose, but that's clearly one change you will see. And the other one is still using carbon dioxide, but in a closed system. So if you seal it or close tight lid so that you do not allow gas to escape, what will happen is you will create a pressure buildup. Okay, as you produce more carbon dioxide gas, it will increase pressure inside the container, so you can use a pressure measuring barometer and monitor the reaction rate. Now lastly, if this is an exothermic reaction, it will release heat energy. If it is endothermic reaction, then it will take some heat away so that the ambient temperature will drop. Now, you should actually know whether it's an exothermic or endothermic if you recognize what the reaction was. This is a reaction between baking soda and an acid, so maybe baking soda and vinegar. So see if you can remember from last year or perhaps earlier in one of your science classes, or you had a chance to mix baking soda with vinegar and observe what happened. So did it release heat energy, or did it take away heat energy, or you had to put heat into the reactions to get it going? Okay.